let's use our fundamental theorem line integrals here. Let's put this to work. And so what we should be looking for to put this to work is we have f is the gradient of some little function f here. So take a look. Let big F of x, y, z is equal to, so there's a vector field 2x, y plus z, x squared, and x. So the first thing that we have to do here is verify that little f of x, y, z, x squared y plus xz is a potential function for f. So potential function just means, how do we do this part here? We just need to show that the gradient of little f gives us big F. And that's nothing more than just computing the gradient here. So the gradient of little f is going to be the x partial derivative here as 2xy plus z. The y partial derivative here is y squared. The z partial derivative here, oops, not y squared. It's the y partial derivative is x squared. And the z partial derivative is x. And yes, this is exactly equal to f. So, so big F is equal to the gradient of little f. F is a potential function for big F here. And I should say, I should point out that I write a potential function, not the potential function, because in general, there could be many potential functions. If we modify this to add a constant on here, adding a constant, when we take the derivatives, the partial derivatives, that constant would go away. So this would also be a potential function. There are many potential functions that differ by a constant. Okay, so we have that, we have found, don't worry about right now where this came from. We'll worry about that in a future video, but this is a potential function. So take a look at the second part here. Evaluate the line integral, the vector line integral over c of f dot dr, where c is a curve from p is equal to 1 minus 1, 2 to q is equal to 2, 2, 3. So what this says here, because f is the thing that we're integrating here, and f is equal to the gradient of little f here, we can evaluate this vector line integral in this way. So the integral over c of f dot dr is the integral over c of the gradient of little f dot dr, because big F is the gradient of little f here. And this is equal to little f evaluated at q minus little f evaluated at p. And all we have to do now is, what is f of q? Okay, we're going to plug in 2, 2, 3 in here for, let me just put this off to the side. Little f of x, y, z is x squared y plus xz. So f of q is 2 squared times 2 plus 2 times 3 minus f of p, what we get when we plug in 1 minus 1, 2 in here, 1 squared times minus 1 plus 1 times 2. And that's all there is to this. So think about how much work this would have been to do otherwise if we didn't have this fundamental theorem of line integrals here. It would have been a lot of work because we would have had to, well, first off, we don't know what the curve is. I'm just saying the C is any curve between these 2 points. So, here is, I'm not going to do this to scale. Let's say here is P and here is Q. I didn't tell you whether C is like just a straight line segment from P to Q, or C is like this, or C is like this here. I'm not telling you what curve C is here. For any curve between P and Q, this is going to be our answer right here. And even though I did tell you C is like the straight line segment from here to here, you'd have to find a parametrization for that. You'd have to find the derivative of your parametrization. You have to substitute your parametrization into your vector field. There's many steps going on here. But this makes our life oh so easy. So this is why we like using the fundamental theorem of line integrals.